Hi there again. This is Ron Wade, Principal Systems Engineer in the Timing Group at Renaissance Electronics, and I'm back with Part 2B of our investigation into the jitter transfer functions of SerDes building blocks. And we will now be looking at the clock and data recovery units, or the CDRs. Just a quick refresher from the last presentation. SerDes building blocks consist of three main parts with which we are concerned in this investigation of reference clock jitter. There's the transmitter PLL, the receiver PLL, and then the clock and data recovery unit. And in the clock and data recovery unit, there are two main types. There's the analog type that recovers both frequency and phase information, and there's the digital phase interpolator type that recovers mainly phase information. We're going to focus on the second one because this is the one that is used mostly in PCI Express. So the simplified block diagrams for clock and data recovery are shown here. On the left is the analog version, which has a complete full PLL built into it to get to the recovered data at the latch. Each channel is able to recover both frequency and phase information. That's a plus. However, each channel requires a dedicated PLL in the receiver, and then analog PLLs don't really easily scale as you go down in process geometries to make your SerDes devices more dense. And then analog PLLs consume more power than digital circuitry, and so there's an issue there as well when you're trying to build large numbers of transmit-receive pairs. And then the plus side again on the analog is it easily supports separately clocked transmit and receive, which is what is used for Ethernet. A phase interpolator approach has a phase detector at the front end followed by a phase interpolator, and this phase interpolator is driven by an external frequency source. So the frequency information for the most part is recovered outside of a phase interpolator based CDR, and then you get the recovered and retimed data out here. So the CDR recovers basically the phase information, but it really can't recover frequency information. There is a PLL that does recover the frequency information, and the good news here is this PLL in common clock systems can be shared across multiple CDRs, and we'll talk about that in a future section as well. So the CDR is digital, and so it scales more easily as process geometries shrink. It also tends to consume less power than an analog circuit, and it's an efficient way to support the PCI Express common clocked architectures, where you'll have a link that has anywhere from 1 lane to 16 lanes of data. So the behavioral CDR model for PCI Express Gen 7 is also the same basic model for PCIe Gen 6. The only difference is in some definitions of frequencies. So for PCIe, the clock and data recovery specification, the CDR specification, depends on not only the data rate or being supported, but whether you're in common clock or IR mode, whether you're using an external or internal reference clock. However, for all Gen 7 architectures, this is the transfer function. It has 3 poles, as you can see by the 3 products that are being multiplied together here. And the damping functions are defined as 0.707 and 1. And then we have 3 frequencies. We have an omega 0, an omega 1, and an omega low frequency value defined. And this phase interpolator CDR is it's all set up to move this sample point to the maximal spot in the eye diagram. So this sample point will move back and forth depending on where the phase interpolator says is the best place to sample the bit stream. So that's what the CDR is actually for. So let's look at the plot for this equation now. And It's the black dotted line. And the thing I'd like you to notice is, first of all, the goal of this CDR was to get to minus 100 dBc at 33 kilohertz. And we did so. Again, similar to the other plots, dBc is over on the left. The horizontal axis is in hertz, with this being 1 megahertz, 1 kilohertz, and 1 gigahertz. So we have all three pieces now of the SerDes building blocks, the TX and RX PLLs and the CDR itself. So now we need to look at how they get combined together to create an overall reference clock jitter transfer function at the receiver data latch. So before we can do that, though, we need to really understand how these components get hooked together in the various clocking architectures. And so the next two sections in this series will be on common clocked architectures and independent reference clocked architectures. So I'd like to thank you for continuing to watch this series, and stay tuned for the remaining parts in this series coming to you very soon. Thank you.